başlayalım. Okay, good morning, everyone. It's my pleasure to introduce our speaker today, Çağatay Yıldız, who is a last year doctoral student at Aalto University in Finland. He's also currently a research intern at Bosch AI in Germany. And before his PhD studies, he got his master's degree from Boğaziçi University, Istanbul, under the supervision of Ali Taylan Cemgil. His research interests include learning unknown differential equations with Gaussian processes and neural networks, latent ODEs, deep generative models, and model-based reinforcement learning. And today he will talk about his recent work on continuous time model-based reinforcement learning. Thank you, Çağatay. The stage is yours.
Thank you for the invitation, and it's really good to speak to such a nice audience. So today I'll talk about our last work, which was published in ICML this year. It is titled as Continuous Time Model-Based Reinforcement Learning, and that's a joint work with Markus Heinonen and Harri Lahtesmäki at Aalto University. Yes. So that's the outline of my talk. So today I have over 50 slides, and half of them is basically background. And I hope that I will be able to keep you, like, if you are able to like digest the background, I guess most of the story you'll already get, and the rest are mostly details that you can also read on the paper. And they are mostly about the dynamics learning and policy learning, and then I'll finally summarize the findings. So let's start with ODEs, ordinary differential equations. An ODE is basically defined as a differential equation that involves one or more functions of a single variable. So this is like the very standard form where we have x of t. Here t is time, t denotes time, and that is the variable, and x is a function of time. And we call that xt is a state, and x dot t is time derivative. So x dot t is also defined as, like, can be written like this. And formally, what it means is that if we take time, like an infinite amount of time, infinitely small amount of time forward, how the state would change with respect to this small change in delta t. So that's basically the definition of ODE. And this is typically given by a function f. So f I will refer as time differential function, or just differential function, or sometimes vector field. It typically takes three parameters. One is the state itself. The other one is like time. This is like the dependent variable and the independent variable. And finally, u here is, let's say, some external control signal, which will, like, all of these will be clear soon. So to illustrate what ODEs are about, I'll use an example, simple example called Lotka-Volterra system. Now, what I'm going to show you is that I have two plots here. On top, I show you the first. So Lotka-Volterra is a two-dimensional ODE system. On top, I'll show you the first state plotted against the second state. And on the bottom, I'll show you both states plotted over time. So here, x0, we have some initial state, let's say, which is the red circle here. And now we have this thing called vector field, or a differential function. So again, it tells us how the state would change over time, right? So it is a function like from R2 to R2. And here, all the arrows basically, like the vector field, like the function f corresponds to those arrows here. So basically each and every arrow means how the function would change at this particular point. And then integration is simply this operation. Now, what's going on is that here we recursively compute this integral, again, forward in time. That means like our particle, like our initial state, x0 moves over time and then follows this trajectory now. And when, again, this is like state one against state two, right? And when they are plotted over time, they look like this, basically. Yeah, so these days, well, xt, from now on, I'm gonna refer to as state solution. And these days, computing state solutions are pretty easy. A lot of libraries like let's say, torch diffec or like torch differential equations packages or SciPy, they have this function called ODEInt, where you input an initial value, differential function, some time, and specify solver, and then basically the library implements numerical solutions for ODEs for you. So basically you just give those parameters as input, and then it returns you this forward trajectory. So this is what ODEs are about. Now, let's talk a bit about reinforcement learning. In reinforcement learning, the goal is to achieve some sort of goal, some sort of like to solve some sort of task, right? And we typically say there is some environment. Here it is the world itself. And then there is some agent. Like the world typically has a certain state. Here it is shown by waves that ST. And then agent looks at the current state of the world and then takes an action. Here A denotes the action. And then the agent basically follows, like the recipe for the agent's action is some, let's say, parametric function, which we also call as policy. So what happens here is that the world has a state, agent looks at this state, takes an action, and then the world moves into a different state, right? So the world moves from S2 to ST plus 1. And then, like, because of this action, we observe some reward at the end. So we assume that the world, the environment is going to return the new state and the reward when the agent feeds a new action. And the goal is to reach like the maximum reward. This will also become pretty clear soon. So what can reinforcement learning do? Well, it could do all sorts of stuff, like it could play computer games for you, it could play Atari, you could solve robotic problems with RL, you could optimize certain things like chemical reactions and then like certain resources in your environment. So RL is like really all discipline, and the problems, RL problems can be divided into like categories in several ways. One could be, for instance, the world states or the actions or the rewards. They could be continuous or discrete. If you are playing chess, for instance, the states are discrete. That means there are like finitely many states. But if you solve some physical tasks, the states are continuous, for instance. So the horizon may be infinite or finite. That means the task may take infinite amount of time, or like it could have some beginning and some end time. And yeah, these are all sorts of different classifications, you could say. And this is like another way of seeing things. Now, because our goal is to do continuous time reinforcement learning. Now, this taxonomy concerns how RL tasks can be divided in terms of like how they treat time. So on the left-hand side, we have really discrete time problems like chess and Go, where basically like each action follows the other one in like certain increments, and the increments is basically up to agent. So if you are playing chess, for instance, you could wait as long as you want, right? And the environment, which is the chessboard itself, would stay as it is without any change, right? So these problems are indeed discrete. And there are also discrete problems which have high time resolution so that they look like continuous. So if you imagine a computer game, what happens is that the game is a certain state, let's say you observe 24 frames a second, then within a second, you would observe, in fact, 24 different states of the same game, like possibly. But because they come so often that you like perceive the game as a continuous thing, but actually it is like a discrete one. And the last category, and this is like the category that we're interested in, is continuous time RL tasks. These are like truly defined in continuous times because they are like mostly like physics related tasks. So if you are trying to solve pendulum problem, or if you are doing robotics, then the time, like in the real world, it flows in a continuous manner, right? That's why such problems should be treated from a continuous time perspective, whereas this hasn't been done for a long while, you could say. Again, this is now the category that we're interested in, and type of the problems that we try to solve are like pendulum, card pulse, or robotics, or like if you go really fancy, even self-driving cars would fall into this category. Now I'll try to compare continuous time modeling against discrete time modeling. So this is a simple task called card poll problem, where we have one card and attached to the card is a poll. And the goal is to basically apply certain actions so that the card would go from the poll would go from the downward position to the upward position. Now, this is again a physical task, and there is a differential equation that defines the dynamics of card polls, for instance. So this is indeed continuous time. So that's the case. And in continuous time modeling, what we do is we treat time as a continuous object. So it could take any value from, let's say, 0 to 5 in this task. And then we say that from one observation, xn, that means like the observation at time tn, from one observation to the next observation, the observation at time tn plus 1, we have an integral mapping. So this is what continuous time models would do. In discrete case, what happens is that we assume that the time flows in a discrete manner, and the observations, as will be plotted here, they basically follow staircases. But I mean, if the frame rate is too high, then effectively a discrete time model would look very much like a continuous time model, in the sense that this grid, like the time grid, would be so dense that we would perceive this as a continuous time model. So basically, this is like the philosophical difference between continuous time modeling and discrete time modeling. Yes, and I forgot to tell you that you could interrupt me anytime you wish, although I guess you would have to speak because I'm not able to see the chat window at the moment. But yeah, so far, reinforcement learning has always been done in this, almost always been done in the discrete time, in discrete world. And our goal is to now do RL in that continuous time setting. Now I'll talk a bit about model-based RL. So again, there are all sorts of RL, let's say, solution methodologies, and the one that we use is called model-based RL. There, the goal is to learn some proxy model for the system dynamics. That means we try to learn some function. Here, the function is f, which is a time differential, because now we're interested in continuous time solutions. We would learn a differential function f that tells us how the world evolves. So basically, given some observations, we try to understand, our model tries to have an idea of how the world basically evolves over time, how it changes. And then we use this, our proxy model, f, the proxy will be shown by f hat or f hat theta, to learn a good policy. So what we do is we try to understand how the world works. And on top of our understanding, we will build a parametric, we will build a policy on top of the dynamics. So that's our recipe basically. And I'll try to summarize the model-based RL workflow. And this is due to Dyson-Roth's Pilko paper, or there could be earlier references, and but this is the one that I follow. So what we do is we initially, again, let's say we try to solve the card poll problem. Initially, we don't have any estimate about it. We have a proxy dynamics model, but it is completely, let's say, because it hasn't seen any data, it is completely incorrect, right? So what we do is initially we pick some random policy function that, let's say, moves the card to the right and to the left, and then we collect some initial data set. And then as long as while the problem is not solved, we proceed the upcoming while loop, where we first train the dynamics using our data set. That means as we collect more and more data, our dynamics model should get more and more accurate, right? And after training the dynamics model, we train our policy model. That means we use our dynamics to build a policy, build a recipe about how to act in that world. This is this last line is all about simulations based on the dynamics, and there is no interaction with the real world at all. And then we use our current policy in the real world, we execute the policy and see if that solves the problem or not. And then as we execute the policy in the real world, we collect like a new data sequence. And then if the problem is not solved, that data sequence is used to train the dynamics model even better. So the idea is that as we iterate this while loop, we would collect more and more data. And at the end, we would train the dynamics models. We would obtain like a better and better estimate of the real world dynamics. And that should help us learn a better policy. Now, in the upcoming slides, I'll summarize this overall thing. And the data sets are typically look like triplets, where we observe, let's say after each iteration of this while loop, we observe one state sequence, one action sequence, and one reward sequence. So how does this thing work is that our agent applies its policy in the real world, policy function pi in the real world, and the real world or the environment returns us some state sequence, here like t+1 observations, plus the reward sequence, where like each state is associated with a reward, and these are like S and R state and rewards. These are given from the environment, given by the environment. And yeah, AT is the action sequence that we specify. Now let's see what this looks like. This is like the very beginning of the while loop that I showed you before, where we apply some random policy in the real world. So our initial random policy is basically the one that basically pushes the card just a bit to the right. So this is like the action that this is basically a 0 to t in a shown in a continuous manner. And then the state sequence that we observe, that the environment returns, basically there's not much going on here so far. And of course, the reward is also pretty low, you could say. So after this, we train our dynamics model, train our policy, and then they execute the policy in the real world again, and then we repeat this, right? After 4 iterations, well, we basically obtain this picture. Now, only 4 iterations of this while loop leads to such a policy function. Here, the dynamics are not shown at all, but the policy that we learn after 4 iterations, it kind of does something, right? It is able to swing the pole, swing the pole to the upright direction, but is not able to balance it. But as you can see, the reward goes up a bit, and of course, our goal is to achieve the highest reward all the time. And then, if we continue collecting more data and then training more and more using, now we have 8 sequences, then the policy becomes much better, right? It almost balances the pole, but not exactly. So we continue iterating, and after the 15th iteration of this while loop, that becomes the picture now. Again, the policy, we are able to balance the pole in the upright position, although it is not perfect. It moves to the right and to the left a bit, but this is a good picture, you could say. So in 15 iterations of this while loop, we learned a dynamics function, which is good enough in the sense that the resulting policy basically solves the problem, or almost solves the problem. Yes, and again, so this was the background so far. Now let's see the details of the model, the details of the methodology, and we will start with the dynamics learning. So again, our goal is to approximate the dynamics using a in continuous time framework, right? That's why we will approximate the time differential function f. And in this work, we choose to use a neural network to approximate the differential function. And this is what people call a neural ODE. And this was published more than 3 years ago. And then our goal is to compute, whenever neural networks are involved in an ODE-based model, then the exact posterior is analytically intractable. So we propose a variation posterior over the model parameters theta here. And this we already proposed like 2 years ago, again, more than 2 years ago. And of course, our goal is to minimize the posterior, like the variation posterior, like we minimize the KL divergence in the exact our variation posterior and the exact posterior, right? This is classical elbow derivation. And then, well, we do some like calculus, and then at the end we observe, like we obtain this lower bound on the marginal likelihood. And the second term here is a KL between our posterior and some prior. This is usually like easy to compute, and the second term is more interesting. This is what we call an expected likelihood, right? And the expectation here is with respect to Q of theta, so with respect to like neural networks parameters, whatever they are. Now I'll open up the expected likelihood. So if you remember, our data set consists of like sequences, right? Let's say each sequence is like up to like time. Let's say like each sequence contains t plus 1 observation. So we need to have one sum that goes over time, and we need one more sum goes over each and every sequence, right? And on top of that, we approximate this expected likelihood by Monte Carlo sampling. That means we need to sample from this expectation, sample from this Q distribution, and then compute this term. Now the so the likelihood basically is like a Gaussian. We choose a Gaussian likelihood model where our goal is to fit the observed data sequences, right? These are SIs here, and again, we are in the continuous time setting, right? So we treat SIs as like state solutions, and so the likelihood becomes like the likelihood would be like the true exact state solutions, or like data points, and our approximate state solutions. Now I'll switch to this for a second. So now this is the term that we need to compute, and this term is basically given by this guy here. So given a sequence, given like an initial value and an action sequence, our neural ODE model is able to compute a state solution for us, right? So it is able to compute this integral where we integrate over, like we integrate, like where the differential function is a neural network here. And for each draw from our posterior, we have a different vector field F, and each vector field gives us a different state solution, or like trajectory sample. So basically how this framework works is that we first draw from our approximate posterior. It gives us like a set of parameters theta, L, and then we forward integrate using theta L, and then that gives us a state trajectory. And the likelihood is basically just the sum between like the state trajectories that we find and the state trajectories in the data set. So basically that's it. And the overall framework is all based on Monte Carlo sampling, and yeah, I guess that's it. So again, the previous slide, I said we have a approximate posterior over the neural network parameters, right? And now this is like where the model gets richer. So where to place the posterior, and like what type of posterior that we would like to place defines, like specifies the model itself, right? Yes. So what I was saying, so if you place, let's say, if your Q distribution is a Dirac delta, and if you place it on the weights of the neural network, then what you obtain is a deterministic, like plain, simple neural network, right? So there is nothing Bayesian going on here. But if you place a Gaussian posterior on the weights, then you would obtain what we call a Bayesian, like a vanilla Bayesian neural net. Or you could place a mixture of Dirac densities, again, on the weights, then you would obtain an ensemble of neural networks, right? Where like each mixture component would give you a different vector field, and then this would like help you maintain some sort of uncertainty over the trajectories. And you could also place your posterior on hidden neurons instead of weights, and then these would give you implicit BNNs or batch ensemble of neural nets. So all of like the last three we try in this paper, and experimentally we find that ensemble of neural nets they work the best, or like the performances are pretty close, but I guess ensembles are the best. So what is an ensemble learning? Like what we try to do in ensemble learning is that we have like a complicated posterior or like optimization surface, you could say, and we have like bunch of particles or ensemble members that we optimize like differently, like simultaneously, but like each and every particle converges to a different mode, or like hopefully converges to a different mode in this complicated optimization surface. Now, each and every one of these particles, if you remember like the 2 slides back, each and every of these particles, they translate into a trajectory sample, right? Like each particle matches a trajectory. And then when you basically put all the trajectories on top of each other, you obtain such a picture. Now what's going on here is that the yellow shows a data trajectory, and the gray curves, they correspond to like each and every ensemble predictions. So with this, we are able to like each and every ensemble member, they agree on the data sequence. So that means like we maintain some sort of uncertainty over the data trajectory. So this is kind of a desired picture. And of course, what is even better would be like if the ensemble members, they disagree outside the data, then that would be even better. But again, that kind of summarizes our framework, where like our posterior now, approximate posterior has like 5 ensemble members, and each draw. So basically, Q theta is like a mixture of 5 Dirac densities, and each sample from the Q theta, it gives us one state trajectory like this, and then the likelihood, for instance, becomes like the Gaussian, some Gaussian between this curve and the yellow one here. So that's what the framework is about. And here I try to visualize what the ensembles look like in the context of RL. This problem is called like an acrobat problem, very much like pendulum. We have like 2 little bars here, and then we push the bars like to the right and to the left a bit. And the goal is to start from this downright position and then to go to upright position. Now, to the right, I show you how the system looks like in like 0.2 seconds increments. And initially, like we are in one particular state, like the system is a simple initial state, right? And then as we like predict forward in time, our model brings some uncertainty like here. So here I visualize 10 different ensemble members predictions. So basically here I had 5 different curves, right? Here, like I have 10 of them, but instead of curves, I show you like what the acrobat system looks like. And there is a little uncertainty, as you can see, at the very top position. And if you integrate like even longer, you would obtain more and more uncertainty. So I guess if you are in the deep world, like if you are doing deep modeling, deep learning, then ensembles is probably the most straightforward and in practice useful method to obtain uncertainty over your predictions. Yes. Now I will continue with post-learning. Now this equation may look a little scary, but in reinforcement learning, or like in post-learning, our goal is to maximize this guy here. And what is this? Is just an integral that goes from time 0 to time infinity. So this is what people call an infinite horizon reinforcement learning problem, where we start from an initial state S0, and then we follow a policy function pi, and here phi corresponds to the parameter of the policy function, and then we execute the policy in the real world until for infinite amount of time, let's say. And then we maximize this term, and the first term here is, let's say, just like some term that basically drops over time. This is what people call a discounting factor. And then like what the term that we are really interested in this guy, which is the reward over time. So what happens is that we execute the policy in the real world, right? In the real world, like the real world state changes. And after each state change, or like maybe smoothly over time, we obtain some reward. And our goal is to maximize this reward. So if you imagine the card pole problem, the reward is maximum when the pole is in the upright position, right? So basically a policy that solves the card pole problem would bring the pole to the upright position and then keep it there until like infinity or until we stop the task. Now, maximizing this term is a little difficult because this integral goes to time infinity, right? This is why many people people have been working on what is called a model-free reinforcement learning, where there are tricks to learn to maximize this term while interacting with the world. So model-free RL, what it does is basically it does not use any like dynamics proxy. It doesn't learn the dynamics, but it directly operates in the real world. And model-free RL, like one of the most popular ways of doing model-free RL is using Q functions. And the details I'm not gonna go into now, but what happens in continuous time is Q functions, they vanish. So all the model-free RL like literature about Q functions, it basically collapses. It basically goes away in the continuous time setting. And also like a large group of model-free or even model-based RL methods, they rely on stochastic policies, where the policy function outputs a distribution over the action to take. But unfortunately, stochastic policies are not available here. And the reason is that we have an integral, right? And the integral, like the differential function itself, should be deterministic. But if you have a policy, then the function that you should learn, the differential function, is also automatically stochastic. So like two major ways of policy learning basically is not applicable in the continuous time setting. That's why we need a new method. So then let's do it. First, what we do is, again, the goal is to maximize this integral. But of course, this integral is, well, basically here, the reward follows, or like the trajectory follows the real world dynamics, right? So our goal is to maximize the reward sequence, or maximize the reward integral in the real world. But we don't know how the real world works, but we are in a proxy model for this, right? That's why instead of this guy over here, we maximize an expectation over Q theta. And here Q theta is again our belief on the real world. And this is what people call an imagination. That means we imagine state trajectories, state sequences, state trajectories, and each trajectory gives us one reward sequence, and then we maximize these reward sequences. We maximize our dreams, if you want to go fancy. Yep, so basically that's it. So this integral basically follows this equation, these two equations, where this one I already showed you. Now the actions in this differential system, they follow this policy function pi. And again, phi's are the parameters that we would like to optimize. So again, we'd like to maximize this guy with respect to phi, right? And here the states, like this integral, how should I say, sorry, rewards are related to states, and states are related to actions, and the actions are related to policy and phi. So this is like how the backpropagation is gonna go, all the way from reward to state, and from state to action, and from action to phi. So again, one problem with the previous write-up was that we had an infinite integral, right? So what we do is we rewrite the integral from time 0 to time h, and then from time h to time infinity in a recursive way. And if you do it this way, then the second integral, it becomes this term. So basically, this is like the overall expression is a recursive writing of what I showed in the previous slide, right? So, okay, that's good. But now, this is like the first trick that we do. And the second one is, again, computing, again, like our goal is to maximize this guy, which involves maximizing this guy over here, right? But again, maximizing this is a challenging task because it is like another integral plus the same term, again, defined recursively. So what we do is we basically terminate the recursion here, and then we say that we approximate this guy with some other neural network. Size are the parameters this time, and now this neural network is called critic. So what it does is it tells you, so by the way, this term is called like the value of state 0. So this is called a value function. So what the critic does is it tells us the value of each state without like computing this difficult to compute term. And then we plug in this guy over there. Now, what we have on the right-hand side is, again, like this is a term that we would like to optimize. And finally, on the right, we have one finite integral, which we can optimize with respect to policy parameters, and another term, which is, again, like a, how should I say this? So in practice, SH, like the last state, like the result of this integral, and this is the input to the critic, right? It is a function, like this is the result of the integral, this is like the end state of the integral, and naturally this is a function of the policy itself. So policy moves the state 0 to all the way, let's say, to state at time h, and then that particular state, the last state, it goes into our critic here. This is why this guy is a function of policy, as well as the sequence is a function of policy. So like both terms are functions of policy, right? This is why we just compute like the gradient of the whole term with respect to the policy, and then that is like the optimization routine. Yes. So again, this is like our optimization goal, and here the input, like the initial input is S0, like the initial state of the system, but we make a little trick here, and instead of starting from the initial state, we propose to like, again, we have a data set of states, right? And we propose to learn the policy starting from any random state in our data set. That means that would help us to learn a good policy everywhere in the state space, everywhere that we visited in the state space. And yeah, basically the actor or like the policy just maximizes this entire term. And the critic learning is a little more tricky. If you remember, like the definition of this nu was, well, the same as this v, right? And in practice, what we do is for a given state S, we compute this term, and then it goes into like here. And then we also compute like the value of state that's given by the critic, and then we minimize this error. So that means we basically minimize the critic's output against the value estimates against this term. But also this definition is a little tricky because this term, like this expectation contains the critic itself. So we kind of regress the critic output against like an integral plus critic output itself. So that is like a really difficult optimization problem, you could say. But in practice, this works. And yeah, and again, all of these are formulated in continuous time, where like we have an integral initially here, like the first term inside the expectation is an integral, and that thing, like the overall framework, it generalizes over the existing policy learning methods where you observe sums here instead of integrals. So if you want to do, like if you take this framework and then replace our continuous time model with a discrete one, then you would obtain like summations here instead of integrals, and the problems, well, like the formulations would basically converge to existing discrete time formulations. Yes, so this part is a little, like the policy learning is a little tricky, but in the paper it should be written like more clearly. Now I'll try to summarize the findings. So the first thing that we did was, so there are those reinforcement learning frameworks like OpenAI Gym or DeepMind Control Suite, where they have, like they implement, let's say the cardball problem, and like similarly some more continuous time physics like control tasks. And what we did was we first checked whether those implementations are good or not. So all of those physics engines, or like OpenAI, GEM, and DeepMind control suite, they, again, as I said before, cardball system is a continuous one, but the numerical solution, we know like how to obtain a numerical solution. And these frameworks, OpenAI, GEM, and DeepMind control suite, they also perform numerical integrations. But then the first thing that we showed was their numerical integration routines are inaccurate. Here, for instance, we take a policy function and then solve the cardball system, like the true cardball ordinary differential equation, and the resulting, let's say, like the so we solve the, how should I say this? So given the true cardball equation, cardball ODE equation, we solve it using a like a good numerical solver, and then at the end, like the poles, like again, like each solution, like each state solution would give us a trajectory over like the pole's position, like pole's, how should I say this? Pole's angular velocity and angle, right? And from the angle, we take the cosine of the angle and visualize here. So the red sequence, in a nutshell, shows how the cosine of the pole, like the cosine angle of the pole, looks like over time, which is basically where this plot basically summarizes the thing where the pole goes upright in 2 seconds and then stays there until, let's say, time 10. But if you apply the numerical integration routines in OpenAI, GEM, or DeepMind control suite, you observe these plots. And what's going on here is that the pole goes to the upright position, hangs a bit there, and then falls down, and then goes up again and falls down again. Again, like here, the only thing that changes is the integration routine. And basically, the integration routines used in OpenAI, GEM, and DeepMind control suite are incorrect. So that means if you train your policy model within these frameworks and then like transfer the learned policy into real world, they would fail to solve the problem. So that's the first thing that we showed. So all the existing RL frameworks which simulate the OD systems, they are basically incorrect. Like they do it in an incorrect way. And then the second thing that we showed was that, so the first equation here shows a discrete transition model where like the next state is equal to current state plus a function of current state and current action. And that's like the underlying assumption in like the state-of-the-art probabilistic ensemble of trajectory sampling method, PETS, I'll call in short. But now the tricky part is that the PETS equation, or like this update equation, is only valid if you observe, if observations, they come in like uniformly over time. So if each and every observation comes in like 0.1 seconds increments, let's say, then what happens is that you train your dynamics model using this vanilla equation, and then your training and test error, they all go to 0, which is great. But if the observations, they are not uniform over time, well, if they are stochastic over time, so if like the time increments, they follow some distribution, then basically this first equation, it collapses. And what people do is they bring delta t, like the time increment here. And then if you do this, then the framework, then the PETS, or like any discrete time framework would work in practice. So this looks like a minor detail, but I mean, without this guy over here, like the framework, like does not work in like more complicated scenarios like this one. So in all our experiments, we use this equation, like this modified approach to compare our models with. And this might be, I have already spoken about this. So what is going on in this picture is that, again, if you solve the cardball system like using, like if you compare the true cardball solution, which is shown by orange here, against our continuous time solution shown by yellow, against the discrete time solution shown by red, we obtain these plots. Now, if you look at the value plot here, like I visualize the position, like the action sequence that they apply, reward, and the value. If you look at the value plot, at the end of the day, this is like in the context of model-based RL, our goal is to maximize the reward integral, or like reward integral is known as value, and value is like what I showed you in policy learning, like function V is the value, and this is what we try to optimize. And the true value, again, orange, and our approximate value, green, they are extremely close to each other. That means our like model estimation is pretty good. And as you can see, the red curve, the discrete solution is like off. And as you like move forward in time, like if you move more and more, and the gap will be, like wider and wider, right? So the value estimates of the discrete time methods, they are incorrect at the end of the day. This is like what we try to communicate here. But then even if you, in practice, what turns out is that even if you optimize your policy using such incorrect values, then you still obtain like a good policy, a policy that's as good as the optimal one. So basically, even if your dynamics estimates are a bit wrong, like here, you still can learn a good policy, and that's a little, let's say, unfortunate for our model. That means like even if you learn a perfect dynamics, then this does not immediately translate into policy learning tasks. Yeah, so these will be pretty quick, I believe. Here, what we show is that we take 3 standard tasks: pendulum, card ball, and acrobat. We take like 3 different approximations, posterior approximations of our ODE model. We take PETs and some other discrete method called deep Pilco, and then we show that on the standard environments, if there is no noise and if the observations, they come uniformly over time. So this is like the most beautiful, like the simplest case, like simplest scenario where all the RL methods are tested, then you obtain practically no difference. Here, you should look at the first, like the top row, and on the y-axis is like the value that we're interested in. So it should reach 1 over time, and like on the x-axis, I show you like models learning over time. And as you can see, like all the models, they converge to like almost the perfect solution in, let's say, 20 or like 25 iterations. So there is nothing interesting going on here. But now what we show is that if the observations, they don't arrive uniformly. So like now what I show you is like on the first row shows the case where the observations arrive uniformly over time. Here the observations, like arrival times, they follow a uniform distribution, and here they follow an exponential distribution. So if the observations arrive like in a stochastic manner over time, plus if you observe some noise here, then what happens is that here blue is our method and the yellow one is PETs. Basically, PETs performance drops significantly. For instance, if you go to the right, like even when there's like a little bit of noise, then the PETs, well, sorry, we should, I guess, go from top to bottom. So if you add a little bit of noise, like both models' performance drops in all scenarios, right? But the drop in the PETs performance is like much more significant. That's like the first message to take. And the second message is that if the observations arrive non-uniformly over time, like here it follows a uniform distribution, here it follows an exponential distribution, then again, the PETs performance, like if you go from here to there, for instance, it drops significantly. So what it means is that if you're a discrete time method, and if you are in like a more complicated scenario where there is some observation noise and the observations arrive non-uniformly over time, then the discrete time methods, they fail. And well, a similar story goes on here as well. But basically, maybe the take-home message is that like the standard RL methods or standard model-based RL methods, they work perfectly in this like scenario where like there is no observation noise and the observations, they arrive uniformly in time in fixed increments, and that's perfect. But if you go a bit wild, then these methods, they fail. But of course, that includes our method as well. But then like the main findings in our paper we have like different plots because the reviewers ask us to like tweak the discrete time method like a bit more. And like another take-home message is that if you like tweak the discrete time approach more and more, if you parameterize, if you like bring more and more parameters, then at the end you obtain basically the same or like very, very similar performance with continuous time methods. So I guess like here I would take either approach. These like do continuous time modeling or like do discrete time modeling with certain tweaks, and then they should work comparably in practice. But I guess it is more interesting to choose like the OD direction and then like do things in a more fundamental way. Yes, and these are my references. And thank you for listening, your attention. That's my website where you can see the paper and my contact information and everything. And I hope you enjoyed. And if you have any questions, I would like to happy to take. Thank you.
Yeah, thank you, Çağatay. So I have a question, but maybe I can first ask our audience. So do you have anything to ask to Çağatay, or let me start? Okay, so Çağatay, you mentioned that these ODs are deterministic in nature. And at the very beginning of your presentation, you showed us a formulation which also includes this external variable u. So I'm just wondering about a more difficult situation, like for example, for this cart pole problem. Suppose that we have an external force, which can be just a wind, which randomly changes from time to time. I suppose that can be captured from this variable u, and like this might introduce some sort of stochasticity, and I am wondering whether this will pose some sort of difficulties to learn such a difficult to model dynamics, especially you also mentioned that these ensemble models work the best, but suppose there are these additional stochasticity, maybe they can smooth out this field a bit more. So I'm just want to hear your opinions on this.
So I think one interesting aspect is that so if you look at this, I need just a second. I'm still learning how to use Microsoft Office tools. But if you look at this trajectory sampling line, so what's going on here is that we draw a trajectory sample first, and then we forward integrate, right? So, and this is all conditioned on a fixed action sequence. So this is now fixed. And then it goes into this integral here, right? So if the action sequence is stochastic, or like if we have a stochastic process over the action sequence, for instance, something like a Brownian motion, let's say, which is like quite stochastic and which can be used to model, let's say, like the wind, then what we need to do is we still need to sample from that Brownian motion or the stochastic process to compute this integral. So that means like when the action sequence is stochastic, this overall framework becomes really challenging. Or of course, like one thing that you can do is you basically disregard the integral, and then you turn this into a stochastic differential equation where you do have some stochasticity. So that's like the first thing to do. And in my experience, when the control signal or like when the external force is stochastic, then like that makes the overall system quite chaotic, I would say. That's why typically optimizing SDEs or like such stochastic models is really challenging, and one needs to be like super cautious about like, oh, how should I say this? Super cautious with like certain model choices. So for instance, neural nets easily, like again, in my own research experience, neural nets easily tries to like overfit the actions or overfit the stochasticity in the sequence. That's why using like an ensembles, or like using maybe like not just ensembles but BNNs, in the sense that like weight space BNNs would be probably helpful to eliminate this like stochasticity effect. I believe.
I see. Yeah. Then, thank you, Çağatay. So, any other question to Çağatay?
Well, thank you, Çağatay, for the presentation. I'm actually wondering, like in parallel to Aykut's question. So, if you also said at some point where, like for the policy learning, the stochastic models are not preferred or are not possible, as if I'm not wrong. But if you just following your suggestion, like action space taking some stochastic form, then the underlying governing equation can be represented by a stochastic differential equation. And by comparing your method, it will simply be the drift term, that is the ODE, that will encapture the main, let's say, the deterministic and the force, which is trying to move, let's say, a certain type of functional parameterization of the wind. But then, in case there is some randomness, that has to be governed by the second term in the SDE. I think there is like a connection between your approach, the ODE type and the SDE type. I don't know if you can elaborate any further insight on that.
Yes, that's a really good point. So,
and maybe one more, like an extra comment on the discrete and continuous comparison. I think on one of your results, it was result 4 or something, you fixed the temporal resolution in the discrete setting, and then your function has no, you have no assumption on the smoothness on the underlying function that you are willing to learn. By this, I think for sure it will not be possible to find out like a good map between the discrete and the continuous. But if you go for like an adaptive setting where you can change the learning rate and the learning step size, let's say, this too will give like some very close or equivalent results. I think in the limitings in this scale.
Okay, let's first let me first try to answer your first question, and then I'll come to the second one. So indeed, like if the actions here are stochastic, or if this function f is stochastic, then this turns into like some form of stochastic differential equation. But now, like when you write out the details, for instance, if the action is not deterministic, but if you have, let's say, a Gaussian, do I need? Hold on a second, so I'll go a bit forward. Yes, here. So let's look at this equation again. So if this is a deterministic function, then this overall integral, well, assuming that f is deterministic as well, the integral becomes a deterministic thing, and we are in the ODE setting, that's great. But if, let's say, if pi is here, it outputs some distribution, let's say Gaussian, and if you sample from the Gaussian here, then the result, like if you do the calculus, the resulting term becomes like a deterministic term plus like some time-related constant plus some like Brownian motion type stochastic term. So that does not immediately translate into ethosense SDEs, because there's like a little mismatch between like the magnitude of the Brownian motion and the time increment. But these are like kind of minor details, you could say. But in practice, one could draw like a, let's say, one could fix the noise that you draw, and then like once the noise, let's say the Gaussian noise is fixed, like once you draw a fixed random number sequence, then overall this thing becomes deterministic again, but given the random sequence. You see my point? So this could be like one trick to turn stochastic policies, stochastic systems into deterministic ones. But otherwise, yes, like it would, if A is stochastic, then that would become some sort of SDE. Does that answer your question?
Yes, partly, yes. Thank you, Çağatay.
And the second one, let me also answer that. If I get you right, so this term here is not fixed at all. So like for each like pair of data points, we have a particular delta t value, right? Like if we know in which frequency, like we know the interarrival times, and then we plug those interarrival times here while training the discrete time method.
No, I think the previous result or the next one, when you show, yes, this one.
This one, yeah.
Yeah, for example, this one, if you have no assumption on the reward or value function smoothness, then fixing, I think you have a fixed time resolution in this plot, basically in the red one. Yeah, that there is no guarantee that the discrete setting can capture. Of course, in the continuous setting, we have the full arsenal of like the continuous methodologies, but the discrete, by properly adjusting the step size, I think you can find some equivalent performances, but yeah.
Exactly. Yeah, like if you tune the step size of a discrete method, then it would finally converge into like the same curve practically, or like it would slowly, and like as you diminish the step size, it will slowly converge to like the orange curve or like the green curve, let's say. And that's basically where we link continuous time methods with discrete time methods. So like take delta t to a small value, and then a discrete time method would become a continuous time method. And that is kind of like one of the messages. But what we prefer is to do everything like in a continuous manner, because anyways, the discrete time methods are just some approximations to continuous time methods. That's how we say it.
Cool, thanks.
Okay, there is no other question. Let us thank our speaker again. So thank you, Çağatay. Yeah, this was a very interesting talk.
Yep, thank you for your attention.
Çok teşekkürler Çağatay.